All right. Good morning, everyone. Isn't this something to be here at CEDAR? Isn't this just wonderful? I'm so happy. I'm so happy. I wasn't at the first one like John Merriweather here. I think I was at the third one, and it's just a thrill to come here every year and see everybody and sort of touch base. So on behalf of myself and Aaron Kirchman, my student who helped me with this work, I thank the CSSC for the invitation to talk about what we've been doing. And I really want to thank Thomas Immel and the ICON team for putting forward such a great mission. I didn't see it coming, and it was exactly what we needed. So this is going to be a spread F talk. So spread F, it's this terrible nomenclature, and it refers to range and frequency spreading of ionograms. First observed in Huancayo, Peru in 1938. Coming up on 90 years. I can't emphasize, this was not only some of the first radar work done for science, this was some of the first radar work done anywhere on the planet. In 1938, radars were going to turn out to be kind of important. And 1938, first pulse radar deployment, Huancayo, Peru, and for geophysics. And so spread F, ionospheric irregularities interfere with ionogram traces. When the Hicamarca Radio Observatory was built, these irregularities, which occur regularly after sunset, were a tremendous source of radar clutter, kind of unexpected, but it turned out to be scientifically very productive. My advisor, Don Farley, wrote a paper in 1970. He said, this is really weird because the irregularities occur in the bottom side of the ionosphere of the F layer, but also the top side. And you wouldn't expect that from kind of gradient drift type instability. So what's going on? That was a real puzzle. Gerhard Herendell wrote a paper. Many people know this work. He introduced this idea of integrating dynamical equations along magnetic field lines in a flux tube integrated formalism. What he was really after, he was trying to argue that effectively the bottom side extends higher in altitude than you might think. So maybe these are all really bottom side irregularities, but that didn't really work out. And what worked out is, Woodman and LaHose just plotted the data the right way. And so I'm showing a picture from their 76 paper where they plotted, radar clutter as a function of altitude and time. And now it's pretty clear what's going on. By the way, this is really cut and paste. These little pieces of paper were cut out and pasted with paste. And that's how they made this plot. But it was the right plot to make because it showed what happens. And I'm sorry I don't have a pointer, but these irregularities start out in really at the base of the bottom side, very low, very anomalously low, and they're reliable. They're practically always there. And then they either do or do not percolate and fill up the bottom side of the F region. And then they either do or do not sort of eject depletion plumes into the top side. And that's really the phenomenon that we're after. These irregularities have all manner of effects on communication and navigation systems and other technological systems, but we really want to understand where they're coming from and perhaps forecast them. This is what spread F looks like from the point of view of the Altair increment scatter radar. It's a really vivid picture of what these plasma depletions look like. And you get a sense of sort of the scale, tens to hundreds of kilometers. These plumes, these depletion plumes, penetrate upward several hundred kilometers into the top side. And you get a sense for the physical scale. This is really what we're talking about. Different instruments reveal them in different ways, but this is really the scales that we're talking about. At Hicamarca, you can do aperture synthesis imaging. These are true images of what the radar clutter looks like in bearing and range and Doppler shift, and you get a sense for, this whole picture is a couple hundred kilometers on a side. So these depletions are little thread-like things, and they meander around in complicated ways, and the flow speeds inside these depletion channels are basically unbounded and can be enormous, supersonic easily and so forth. At the leading edge of the depletions, though, those speeds are bounded by inertia. And so you have a kind of funny dynamic where you have very rapid flows in the channels, and then at the top you can have bifurcation and very complicated sort of meanders and things like that. And so it's really interesting to watch these things develop. But very fine scale structure in here, ultimately, even at the scales that are required to give rise to coherent scatter, which the radar sees. So it's too bad I don't have a pointer. We'll just have to do our best. After Woodman and LaHose did their work, theory followed very quickly, and our community was full of people who understood fluid dynamics and plasma physics very well. And the way the theory works here is you work with the fluid equations, and you combine continuity momentum equations for electrons and ions with Poisson's equation. You get a system of equations. You assume solutions of the form e to the I omega t minus I k dot x, omega is the frequency, the complex frequency, and k is the horizontal wave number. And you work and you work and you develop this, which is a second order ordinary differential equation in the vertical. And maybe phi here is the electrostatic potential. And given appropriate boundary conditions, this is an eigenvalue problem. So there are going to be certain, eigenmodes that, discrete eigenmodes that satisfy this. That's the shape of the potential with height. And each one of them has a discrete eigenvalue that goes with it. And the eigenvalue is the complex frequency that has the growth rate, which is its imaginary part. So it's an eigenvalue problem, and then you look and you see these auxiliary variables P and Q are complicated. So this is something we have to solve computationally. It's a challenging problem to solve. And in these formulas, there are some terms here. There's n, which is the plasma number density as a function of altitude, and there's v, which is the horizontal flow speed as a function of altitude, and ion-neutral collisions are in here and so forth. If you assume the velocities are uniform, this boundary value problem is exactly the one that describes Rayleigh-Taylor instability that fluid dynamicists know about. And if you assume all the terms that involve the number density and their ratios are uniform, this is exactly the system of equations that is Kelvin-Helmholtz. In nature, nothing here is constant. And so you have this kind of hybrid problem, and you can solve this boundary value problem and find the fastest growing normal modes. And the problem in the 80s was it turned out that the growth rates are pathetic. They're very, very small, and with e-folding times that are of the order of an hour or more. And yet we know that our regularities go from nothing into penetrating the top side in an hour. So what's going on? This is a real quandary. And rather than solving it, the community just kind of moved on, because at about this time, numerical simulations were coming around. And so the emphasis really switched to numerical simulations, and the theory was kind of arrested here. You can apply Herendal's flux tube integration to this formula if you want to. It doesn't make the situation any better. The issue is resolved in this way. This whole equation here is an operator L operating on, say, the potential. If L and L complex conjugate commute, then the eigenmodes that you find here are normal modes. If they don't, they're not. And if the eigenmodes aren't normal modes, you can forget the whole thing, because it turns out that the eigenmodes are not predictive. They're not reliable tools of wave growth. And a paper that I cite here worked on this. This is something that's well known in fluid dynamics. If the system isn't normal, then even if all the eigenmodes are damped, you can have growing wave solutions. And not just have it, it can happen commonly. And this system will not be normal if there's shear flow, if there's altitude variations in the horizontal flow. And in the equatorial ionosphere, there is. It's just endemic. It's there because of the imperfectly efficient dynamo. So this just isn't going to work. Not rigorously, not quantitatively. By the way, you probably shouldn't use Herendal's flux tube integrated formula here. In warm plasmas, the magnetic field lines really aren't equipotentials. The potential structure is quadrupolar and complicated, and really what you have to do is numerical simulations. There are analytic techniques that you can try, but numerical simulations are the way to go. So I'm showing you simulations from our code. It's a 3D code, and it has a true 3D potential solve in it, which I think is important. And on the left-hand side, I'm showing 35 minutes after sunset what irregularities look like. And what you see is lots and lots of waveforms growing in the bottom side. And the upper panel on the left is number density. The lower panel is current density. And it turns out that there are very strong vertical currents that are flowing associated with the imperfectly efficient dynamo. And those are strong enough to give rise to irregularities that form at the base of the F region. And these are very fast growing, and they're ubiquitous, and they form almost every night. And the simulation picks that up. If the background zonal electric field is sufficiently large, these irregularities will grow and percolate and occupy the entire bottom side F region. The zonal electric field, which is the same as the vertical drifts, undergoes an enhancement every night around twilight called a pre-reversal enhancement. If that's large and sustained, the bottom side F region will be populated with irregularities. And then if the irregularities get sufficiently high altitude, gravity will sustain them, and those zonal currents associated with gravity will sustain this instability, and things will keep going regardless of what happens to the background electric field. So this tends to be bimodal. Either it happens or it doesn't, and the key factor seems to be the zonal electric field goes through a large pre-reversal enhancement that's sustained, that doesn't reverse too abruptly, and if that happens, then the bottom side F region and the top side F region are populated with irregularities. That's what the code says. All right, this is a talk about ICON. And what we thought we would do is use the ICON mission to test out the numerical forecast code. And the way that we're going to do this is we're going to select data, select orbits very carefully. So this is just for the month of October 2022. I'm taking this as an example. What I did is I found all the occasions marked by blue symbols here where the satellite at twilight was very close to the magnetic equator and in a position to measure everything that we needed to know to force a simulation of irregularity growth. And then an orbit later, 105 minutes later, the red spots indicate the satellite returning to the same longitude sector, where we'd be in a position to diagnose what happened. So we had criteria for finding these orbits, a number of things went into the criteria. The blue spots are where the forecast will be made, where we'll scoop up all the information we can to parameterize the forcing of the simulation code, which will run for 105 minutes. And then the red spot is where we do the assessment. The satellite returns to the scene of the crime, and we see, did irregularities reach the satellite's altitude, 590 kilometers, or not? So that's the question. It's a very simple forecast metric. Based on the drivers that we can infer and parameterize, do irregularities reach 590 kilometers or don't they? That's the test. Easy to state. And here's the way it's going to work. Without a pointer, it's really difficult, but I'm showing number density measured by ICON in the upper left corner, vertical drifts in the upper right corner. Lower left corner is horizontal winds. The horizontal winds come from the MIghty instrument, the vertical drifts and the number densities come from IVM, both really solid instruments. And the blue lines on the left are when we acquire the data that we need to populate and force our model. And in particular, on the upper right-hand curve, you can see around the blue line the pre-reversal enhancement of the zonal electric field. It's this upward and downward going curve. That's going to be the main driver of knowing of the instability. At the same time, the MIghty winds are telling us how the dynamo is working, and we're going to be able to extract from that the vertical currents that sort of jumpstart this whole process. So between the MIghty red line, thermospheric winds, and the IVM vertical plasma drifts, we have enough information to parameterize, to initialize and parameterize our code. Run it for 105 minutes and see whether or not irregularities are detected or not. So the red lines here show what happened when the satellite returned 105 minutes later. And in this case, they were spread out. There's big, rapidly ascending little channels in the vertical drifts and deep depletions in the number densities. So this is a case where, yes, spread up occurred. And we have lots of instances when we can try this. So here in March are 7 times when ICON flew through a region of space in an orbit later, spread up irregularities were there. And here's what the simulation code said should happen. And in all cases but one, irregularities reached 590 kilometers within 105 minutes. So we have one missed detection. It was close, it almost made it. It was a few kilometers shy, didn't quite do it, but nope, we have to give ourselves a fail. Here are 7 cases in March when the satellite did not encounter irregularities 105 minutes later. And the simulation code got that right, except in one instance, where 105 minutes later, the irregularities just barely made it to 590 kilometers. So we have to give ourselves a fail again. But in total, out of 14 attempts, 1 false alarm, 1 misdetection, and all the others were right. So came back and did this in August. 1 misdetection. Come back and do this in October. 1 misdetection. So all in all, about 50 at-bats here made the forecast accurately in all but 4 cases. So I think that's pretty good for government work. And I think that's a pretty fair way to test out a forecast strategy. So, in summary, what I would claim on the basis of this studies and others, that I think the instability physics is sufficiently well understood at this point for us to anticipate irregularity growth and development in the post-sunset equatorial atmosphere. These are all quiet time days, by the way, not getting into storms, but for the most part, quiet times, I think the physics is pretty well understood. That just moves the problem along, because in order to drive our simulation, we need to know the initial conditions and the forcing, and now we have to forecast that. But at least using a satellite like ICON and the instruments that were on it, there's sufficient information to forecast using the persistence of the measurements whether or not irregularities are going to be present in the subsequent orbit. Longer range forecasts are going to require some method for forecasting the pre-reversal enhancement, and I think that's where the problem lies today. If you want to understand variability in equatorial aronomy, you have to understand the variability in the PRE, a problem that was a big one when I was a student and is today. I have to say a few words about ground-based instruments in Hikamarka. We can do the same kinds of forecasts with Hikamarka. Hikamarka has undergone a huge series of upgrades thanks to the NSF in the last few years. One of them is we have solid-state transmitters now that will run 24/7. And that's what we're doing. So we're accumulating data sets, enormous data sets now, and we're using this forecast methodology with those data. And spoiler alert, it seems to work. The ionospheric model that we've been running here is computationally expensive, and it runs much slower than real time, so not much of a forecast tool there. But I think yesterday, Aaron's paper, where he describes a machine learning surrogate, came out, and that works. And the surrogate does these computations in seconds. So score one for machine learning. It's a really nice paper. I hope you'll take a look at it. And I would say, if you really want an operational forecast capability, consider strings on a Perl, some CubeSats with some electric field instruments on them, and just use the persistence of the PRE to make a sequence of operational forecasts. I think it's a strategy that at least deserves some consideration. So that's my story, and I'll stop there and be happy to take any questions you have.
Dave, this is really great to see the progress from spread F theory and observations actually coming forward to being a case where it can be predicted. I just want to say two things. One is just tell everyone it's 590 because that's the altitude of ICON.
Yeah, right.
And had you had a satellite, say, at 400 or something, you would have had, I think, different statistics.
Sure. Yeah, absolutely.
Right. But then my question is, you said, did spread F occur? You must have had some criteria. Were you looking for a depletion that was a certain, like an order of magnitude or a little blip, or what was your criteria?
It's pretty obvious. If it's there, the number densities drop by a couple orders of magnitude, the drifts, move up to hundreds of meters per second. It's pretty obvious. It was chi by eye, but it's not subtle.
The 1938 image you show from Booker and Wells, underneath it said February 1938 when they made the observation. It was published in June. So you make measurements in Peru, and somehow they get back to England, and it's published, which I find kind of cool.
Yeah.
And then as far as the physics, you focused on the PRE here. Also low solar max or solar conditions. You see a lot of post-midnight spread F. That's yet another thing that we could look into.
I don't mean to suggest that we understand everything, and post-midnight is very problematic, and there didn't seem to be key, obvious signatures in the ICON data that clued me in on a way to predict that. You have shown horizontal winds can be very destabilizing.
Meridional.
Horizontal meridional winds, convergent, can be very destabilizing, and I think that's a great place to look. There's many things we didn't talk about here. Sporadic E layers, MSTIDs, lots of different things. I do want to say one thing about Henry Booker. So 1938, he's in Huancayo using a pulsed HF 30 megahertz radar. Tide turns, he finds himself in England, where he contributes to Chain Home, pulsed 30 megahertz radar. You connect the dots. I think there's some broader impact here, and we can't overlook the fact that the things that we do experimentally can really matter.
So you said that the instability physics can be replicated through the modeling sufficiently, given we have good initialization and forcing. So from your perspective, what are the main constraints from initialization and forcing that may preclude accurate replication of these instabilities?
Yeah, I mean, so we have to make a huge assumption here when we import these electric fields, whether they're coming from the satellite or coming from the ground base, which is we assume they're frozen. In other words, that there's a one-to-one correspondence between longitude and local time, and that's not true. And what I'd really like to do is have a way to measure the evolution of the forcing in space and time independently, perhaps with arrays of instruments along the ground or multiple satellites in space. I think that's the main limitation. Okay, great.
If everybody could thank one more time Dave Heisel from Cornell. And next up now, we have our second science highlight from Aaron Bukowski from University of Michigan. And applaud for him too.
Awesome. Hi, guys. I'm Aaron Bukowski. Thank you so much for this opportunity to come here and talk. My title is coming up. It was made before I started doing the work. This is a maybe 2.5-week side project that I did on looking at driving SAMI 3 with TiGCM and GITM with both of those neutral atmosphere models driven by the exact same auroral and precipitation models. Thank you also to every co-author that I've worked with on this. A couple of them are here, a few of them aren't, but thank you if you are. Got it, cool. So executive summary, this is what the goals of the project were when we started, and then also what was done. So we wanted to run GITM and TiGCM with the exact same drivers, the exact same indices files, everything the exact same. Similar enough horizontal resolution, similar dates with TiGCM having the caveat that it has a lot longer of an initialization time. Using default settings whenever possible and whenever is appropriate, and then to look at how the neutral atmosphere and the LSTADs and the LSTIDs develop, and then drive SAMI 3 using both of them. We'll get into that later. What was done was a decent amount of modification to TiGCM. Everything is totally isolated. Everything's blocked by guards. Nothing actually changes. If you run TiGCM normally, you won't touch any of the code that we have added to it. So all of the standalone and prior model behavior is as it was before. We have a model agnostic electrodynamics library that we've developed at University of Michigan, available on GitHub. We have ported it into GITM, TiGCM, and IPE, more to come. With that, we also do readers, and for this study, we're going to look at 2 storms, one during solstice, one during equinox, both during relatively low F10.7, both with somewhat strong of an IMF, but just standard signature, not too intense. On the left, we have the 2013 317 St. Patrick's Day storm, and on the right, we have 2015 in June. Talking about the actual models, the difference between GITM and TiGCM everyone talks about is one is hydrostatic, one is not. That just means the vertical coordinate is different. One uses altitude, one uses pressure. They have different approaches to how they determine their resolution. They do very similar dynamo calculation where they're both in 2D. GITM does a apex field line integration. GITM is also part of the SWMF, a modeling framework. TiGCM is part of MAGE, different solver schemes. SAMI 3 is different. Field aligned ionosphere, doesn't model neutrals, only ions. Doesn't model any of the neutrals by itself. You have to use empirical model or read it from a file, which is what we've done. Reading one way, just reading them in SAMI every 5 minutes, where densities decrease hydrostatically, velocities are constant above the modeled altitude domain because SAMI 3 extends to a couple hundred RE sometimes. SAMI 3 also has a different dynamo than the other 2 models. In terms of the empiricals, here's where the state of things is right now. The orange ones are what we've ported into electrodynamics, what some people are calling MILE. I can't use that name. I don't know why. It doesn't sit right with me. Weimer is the only one that's common between the 2 of them. We have FTA, FRE, and Ovation are all in electrodynamics. Emory or Roble and Ridley and Helix are only in TiGCM, also in WACMX, just NCAR-specific models. Here we see the inputs, outputs, some of the Ovation features and some of the AMI features, reading electrodynamics from file, are not available for TiGCM because of the way they handle the precipitation, but it could be. This is a list of the runs, the combinations of the empirical models. Since we're doing a one-to-one comparison, we want to use the exact same drivers. So that is FTA and FRE. Those are the only two that are common between the two. We also did TiGCM runs with Emory with their default Aurora model, just as a baseline. The Weimar implementation we're using here is the same in both of them, less than like 1% different. There's extreme that are 2% different, but it's almost the exact same. Not all the TiGCM runs finished. Getting into the caveats, I don't know what I'm doing with TiGCM. I ran it for the first time 2 weeks ago, and I haven't talked to anybody who has worked on TiGCM about this project. So would appreciate advice. Some of them were potentially maybe physics errors, especially in the 2015 storm. Some of them were just file write errors, so that's not anybody's fault, but the computer that I was running on. SAMI3 results are only shown from GitHub. I figured out what the issue is. I don't know exactly why yet. Elephant in the room, why didn't we take Helix? Why didn't we take Roble and Ridley? One, licensing. Two, the outputs of Emory depend on which potential model you use. The outputs of Helix would depend on which Aurora model we use. So the Helix potential can only be used with the Emory Aurora. And here we have on the right-hand side the flow chart of the order in which things get calculated, and you can see where the potential boundaries are found when you're using Helix and where the cross-tail potential or cross-polar cap potential are calculated and how that's handed off between everything. So in the future, maybe we can take it, maybe we can rearrange things, but we need permission, which we haven't gotten yet. In terms of how the implementation is done, we left TiGCM alone. If you want to use the electrodynamics that we have, we run it at the end, we replace the values, deposit the precipitation, use the potentials, but that way we don't guard, that way we can still use all of the native TiGCM functionality like the SAPs, the other auroral types, let that all get done, and then not touch it. Here's what the aurora look like, quite similar. Here we can also see why we had to do it this way, because TiGCM also calculates the cusp, the soft electrons, and polar drizzle. And that's over on the right-hand side. That's the total energy flux minus the energy flux of the aurora. We only replaced the energy flux variable, where there's also efflux 1 and 2, maybe 3. So that's just a quirk of the model, quirk of the implementation. So the runs that we're actually comparing to GitHub are the ones with FTA only, where we turned off the cusp, the drizzle, and the soft electrons. Interestingly also, FTA is driven by different inputs, so we have substantially more electron flux, energy flux, than from the Emory model, and that is especially seen here. Dense plot, red line is Emory, and that's just from the TiGCM. This is hemispheric power integrated from the energy flux. There are 2 lines of TiGCM. One is with FTA, one is with FTA only. That's without the other precipitation types. Caveat, they're small. It's like 5%, but it could matter, so we turned it off. It also changes the signature of the storm because FTA is driven by AE, where Emory is driven by IMF and KP, cross-tail potential, et cetera. This is a TID talk. They're back to Dave's talk, where we change topic halfway through. Here's what the TIDs actually look like. Be great if everything could play. Help. Do you know how to play the other 2 movies? Right? That's what I checked before I got here. I had the times synced and everything. It's all right. So on the left, we have GITM and FTA. In the middle, we have a TiGCM FTA with the other two precipitation types. And on the far right, we have FTA only from the TiGCM. The top is the joule heating, altitude integrated, in the exact same units between the three models. Perfect. On the left, we have the GITM outputs, and we can see that the TADs are slightly smaller. This is just total neutral mass density at, I think, 450 kilometers. We can see that things are a little different. They're quite similar, but we can see that all of this propagation is happening from exactly where the joule heating is happening. We can see that in the joule heating plots on the far left, most of them actually, there's creases, there's a lot of mess, and that's why TiGCM has its auroral and precipitation models coupled so tightly, is because you have these creases that form and heating that is somewhat less realistic, but just a modeling study. We are just looking at what happens when we change these two knobs. Now onto the work I was actually contracted for. LSTIDs and SAME3. GITM only extends up to maybe 800-ish kilometers, where the ion-neutral collision frequencies are negligible. So the TIDs up there are definitely not driven by the neutral atmosphere. LSTIDs don't really propagate. They're not necessarily waves. They're the ionospheric manifestation of the waves in the neutral atmosphere. So one of the big findings is the presence of LSTIDs up at these really high altitudes, and that's just due to the equipotential field lines. It's clean, symmetric, and yes, times are synced. Down at the bottom is kind of an interesting case where the amplitude seems to flip. This is something we spent a lot of time trying to actually figure out, is why at the very bottom side of the ionosphere you have the opposite sign of the perturbation that's happening up above it. It's just because the atmosphere is getting raised. So where you have a peak, if you have your electron density profile, if it shifts up above the F2 peak, you will see an increase. Below it, you'll see a decrease. And that's exactly what we're seeing here, is just the height profile shift. Why no SAME3 runs with TiGCM? SAME3 didn't survive. Not a TiGCM issue, SAME3 issue, which SAME3 doesn't like crashing. It's uncommon like that. It's probably due to the lower atmosphere. I just found some issues that seem to happen only in the northern hemisphere that later propagate across the field line into the southern hemisphere, where there's just a tiny peak of electron density, and I don't know exactly why that's happening. We are going to figure it out, but we did everything the exact same. Here on the left, we have the neutral winds from GITM and TiGCM at about 150 kilometers. We can see that the profiles are somewhat similar, but quite different. On the right, you can see that the TiGCM electron density is 2 orders of magnitude higher than in GITM, and it's only in the auroral zone. So it's definitely not a numerical issue. Something we'll figure out. It won't take too long. More thermospheric results. It seems that GITM gets hotter and stays hotter than TiGCM. Why? Not exactly sure yet, but we will figure it out. TiGCM also seems to be cooling off faster over altitude. So on the left, we have the neutral temperature. In the middle, we have neutral temperature. Left is at 120 kilometers, middle is 250, and the far right is at 450 kilometers. In each of these 3 blocks, the leftmost is the TiGCM with FTA and the extra precipitation types. The middle is FTA only, the far right is GITM, and the top is the 2013 storm, the bottom is the 2015 storm. You can see that GITM seems to have a stronger hemispheric asymmetry, whether that's physical or not, beyond the scope of this talk. Again, modeling study, we're just turning knobs and seeing what happens. Eventually, this will be validated against data, and we will come up with which is not necessarily more accurate, but more reliable, in which, which heating profile is more physical, which is demonstrating the hemispheric asymmetries closer to what we actually see in data. With that, conclusions, they're simple. Thank you guys for coming. Scan the QR code if you want to see the TIGCM version. It is up to date, it is working. Let us know if you have questions. If you've run TIGCM, find me, because I need help. Thank you. Yep.
Here.
Oh, thank you. You mentioned about interhemispheric asymmetry. Gideon shows a little bit higher interhemispheric asymmetry than the other models.
Yes.
What is exactly the reason for this happening? Thank you.
That is an excellent question. We're not exactly sure. So the weird thing is that we're looking just in the polar region, they're driven with the exact same drivers. So if I had to guess, it's due to the precipitation, where GIDM does a full energy flux. It decomposes a Maxwellian or otherwise into individual monobins and then deposits that, whereas TIGCM just assumes Maxwellian and deposits it, which has been shown to get deposited a little bit lower. I'm not entirely sure. It could be also that since we're looking at a storm almost exactly at the solstice, that the reference altitudes are, I don't want to say not right, but may not be as reliable at the polar region as in the equatorial region. So something that we'll need to look into. Thanks.
So one thing that's always concerned me is about these kind of simulations that you're using these nice large-scale convection patterns like Weimar or something, and the same thing with the precipitation, and you're applying them theoretically to a storm based, I guess, on IMF or something like that. But in reality, the convection patterns and the precipitation patterns are exactly the opposite of uniform, because there's all these beautiful mesoscale structures. So the joule heating's all really localized, and and it's all varying as a function of time, and a lot of the variations can't be related to the IMF. So I'm just sort of curious, what the resemblance of what you're doing with these large scale is to reality versus what we could do with more realistic potential. So and how that might compare with the real data and things like that. So
yeah, no, that's
just floating around in my mind.
No, that's a great question. And that's one of the reasons that we decided to go with, we need to use the exact same empirical models, is because we need that one-to-one comparison, because we know that there's all of this uncertainty floating around. If we go back to the hemispheric power, for instance, wildly different with Emory and with FTA. What we have the ability to do now is to use outputs from an MHD simulation like the FSWMF or MAGE and drive with AMI files. So we will have a really, really detailed precipitation pattern and a really detailed potential pattern that is physically consistent and actually justified. That is one of the next steps, is to actually do that and to drive the models and see how things behave.
There'll be some points when you get enough super darn data that you could get some pretty realistic two-dimensional patterns and see how they compare to whatever it is you're
Exactly.
using. That'd
Yep.
be kind of fun, yeah.
Yep, thank you.
If everybody could thank Aaron for his wonderful talk. And next up, we will be welcoming Toshi Nishimura from Boston University, who will be speaking about GGR editors, update on the journal's current status, and speaking in his status as a GGR editor. This is forward, this is back, and I'll give you a 5-minute warning.
Okay, thank you. All right, so I'd like to thank the steering committee for giving us a chance to talk about JGR. My name is Toshi Nishimura. I'm one of the new editors in JGR. So I'd like to take this opportunity to talk about the status of the journal and some useful information for the authors and reviewers. As you may know, JGR is one of the AGU journals. So it's our community's journal that's dedicated to publication new and original research in the broad field of space science. So pretty much everything CEDAR does is relevant for JGR. Because many students are in the audience, so I'd like to begin with a very brief background about how the papers are handled, and then we'll talk about more specifics. So once the authors do research and submit papers, and they come to editor's assistant to get quality checked. If there's no problem, that's passed to editor-in-chief, and editor will be assigned to your paper. Then the editor will assign reviewers. The reviewers will submit reviews to the journal, and the editor will make a decision. If the decision is to revise or reject, and then the paper will be sent back to the authors. If the decision is accepted, then it's going to be published. So with this framework, so let's talk about some details of the journal's status. So this is a hopefully useful chart summarizing the status of the many journals that include a space physics component. The second column is the number of publications per year for the papers related to our field, space physics papers. And by looking at this, JGR is by far the most popular place for the authors to choose. So JGR is a good place to submit for broad readership. And also JGR has a pretty good acceptance rate. Many journals, if you look down below at the third column, have 50% or below of the acceptance rate. It's very competitive. Particularly GRL and AGU advances have high standards, but JGR is not trying to meet that model. Though if you do good research and the reviewers are satisfied, then your paper will be published. And also JGR is trying to make a timely decision. Many journals take 2 months or so to get results, which can be frustrating, but now JGR takes 46 days or so on average. It's really interesting that sometimes it's faster than GRL, so full papers can be reviewed very quickly. So those are the good benefits for authors. And the other metric to think about is the publication fee. Many journals have shifted to the open access model, so that's really driving the costs up for publication. That's a problem for authors. But JGR is one of the few journals that still maintain the subscription-based publication options. So if you want to reduce the cost of publication, you can choose that option. Then many institutions still maintain the subscription-based subscriptions library. So you can still read papers, and after 2 years, your paper will become open access as well. Okay, so let's get into more specifics of JGR. This slide is not specific to JGR, but applies to many AGU journals. So many authors choose research articles as an article type. That's a standard one. If you do new science, you choose this and get published. But you can also choose data articles and methods. And if your advance is not about science, but collection new data or development new methodology, you can choose these options. The benefit is that you don't have to report new science. You just need to apply to some space physics problems. So particularly if your reviewers don't agree with your scientific advances, which is, by the way, the most common major comments from reviewers, you have an option to switch to these article types, and then your paper will still get published. The last one is less known, but JGR also publishes review articles. So if you have great ideas about reviews, please consider JGR as a place to submit your papers. And also let us know if your colleagues have some ideas too. AGU journals accept your proposals for special collections. Particularly, here are 5 examples going on at JGL now. Special collections feature some particular topics, significant events like May 2024 storm events or prominent theme. So like a new satellite mission like Tracer get launched, so that's a good reason to propose special collection. There are prominent themes going on in the community like machine learning, and there are lots of ionosphere papers published in the low latitude ionosphere special collection now. So if you have some ideas about special themes that can be based on workshops or any activities going on for a group of scientists, please consider to submit special correction proposals. The benefit is that that creates coherent activity in the community, and that tends to attract more attention and also citation. So that's a benefit for the authors. Okay, so from here, let me answer some of the frequently asked questions. And one of the biggest questions we receive is why papers take so long to get reviewed. So let me explain why those things happen. The biggest challenge every journal has is to secure reviewers. In case you haven't thought about how often reviewers say yes to a review request, it's only 30%. It's surprisingly low. So that means 70% of the time the reviewers say no or even don't respond to a review request. So this one takes time. Reviewers may request to extend reviews. That's perfectly fine. We provide a week or two extensions for busy reviewers. But the harder ones, the reviewers sometimes just disappear. They accept but don't submit reviews. So this significantly delay the process. And even if we get 2 reviews, sometimes we fall into a very difficult situation. Review one says accept, review 2 says reject. Then what can we do? So we step in, and we solicit third reviewers, and we contact reviewers asking for why you said these things, for clarification to the authors. And editors and associate editors also provide extra comments so that the authors can understand how to revise the papers. Okay, what can authors do to publish the papers more smoothly? The first one I would say is to suggest more than 3 reviewers. So 3 reviewers are required to suggest, but like I said earlier, most reviewers say no to review requests. To increase the chance of selecting reviewers you want, you can suggest more reviewers. But don't list close collaborators or people who don't have relevant experience. And also clearly state the scientific or technical advances of a paper. If the key points or abstract don't clearly speak what your paper is accomplishing, the reviewers often say, no, there's no significant advance. So to avoid those major comments, so please make your points clear and upfront. Resubmission from other AGU journals are very common. We make independent decisions regardless of what the previous journal said, but please write a response letter to a previous review. That helps understand the status of your paper. And also feel free to contact us if you fall into some situations where you don't know how to proceed. So like reviewers sometimes ask unreasonable comments, like do a completely new simulation, analyze completely new data set. Do we really need to do that? We sometimes get those kind of questions. We're happy to sit down with you to see how we address those reviewer comments. And also we have some suggestions to reviewers. First of all, we really thank your service to the community. Without reviewers, we can't really publish papers. And we understand reviewers are busy, so if you can't review, please feel free to decline, but please suggest alternate reviewers, and that's really helpful. And that's much more helpful than not responding to reviews. If you don't respond to review requests, we are waiting for your response, so that's gonna be a big delay for the authors. And if you request an extension, if you want to request an extension, that's perfectly fine. If a week or 2 of time will help you, that's much more appreciated than declining review requests. We are always looking for new reviewers, particularly for early careers who have never been contacted about interest in reviewing, please let us know. Very quickly about AI usage, this is a growing question, so let me briefly address that. Authors can use AI tools under certain situations, like checking your grammar or using a research methodology, but AI tools cannot be used to write a significant part of a paper. Of course, it can't be used for fabricating data. And authors are ultimately responsible for the output of AI tools. And the journal may reject suspicious papers, so please be careful about their usage. The last slide I have is from the slide that I was asked to put out from AGU Books. At AGU also published the books, so if you have more ideas than the review paper, please contact these editors listed here. One of them is Bear Garrett-Lacourt, who is a steering committee member in the CEDAR community, so it's easy to reach out. So this is a good place to broadly disseminate what the big collection of work you are doing. So that's all I have. So in the bottom line, so if you have any questions about your paper, the paper you're reviewing, or future papers, or comments about the journal in general, feel free to reach out to us. Thank you for your attention.
Thank you for speaking to us today. It's expensive. I couldn't get past the $4,200 to publish an open access paper. Why is it so? I was just, maybe it's, you don't know, but maybe some insight on where the costs are, like what, why?
So of course, I'm not deciding these numbers, but many journals shifting this model because open access is a keyword, so that's coming down from upper levels. So papers product need to be accessible immediately to people, to taxpayers in general who don't have subscriptions. So that's why the publishers are trying to diminish the subscription plan. So, but trying to maintain the revenue, I believe. So that's why they're trying to collect fees from authors instead. So that's a burden for authors. I'm also writing papers, so I exactly know how you're feeling. But JGR is trying to provide options for authors so that you don't have to pay $4,000 to publish a paper. And also, I think I need to mention this too. So for people who don't have enough money, so like people from developing countries, there are an option to request fee waivers or fee reductions. So we provide opportunities for broader range of authors to publish papers.
Have you ever considered dropping from 2 reviewers to 1 reviewer?
We try not to, but there are some circumstances where we have to go with 1 reviewer, particularly when the reviewer 2 agrees to review, but they don't send the review back. We try to find a 3rd reviewer, but particularly in summer, it's really hard because many people are traveling. And if reviewer 1 is a really good expert of the topic and provide good review of the paper, there are situations where we go with just 1 reviewer.
Some journals years ago just dropped it to 1 reviewer to speed things up. So.
Oh, yeah. So APJ does that routinely. JGL still maintains a 2 reviewer standard to make sure that the quality of review is good, but and we go on a case-by-case basis.
We have time for one more question.
Hi, Spencer Hatch from the University of Bergen. I wanted to represent the European viewpoint since I've been in Norway for about the past decade. And I just wanted to say there's a shift among colleagues that I speak to. Many are choosing not to submit to the JGR journals specifically because of the open access issue. And so a lot of us have been submitting to, in particularly, Annales Geophysicae, or Geophysica, because you see that's one of the lowest costs. But just to say, if there's any sway you have with people at the top, maybe it's worth pushing for more open access and possibly lower fees. I think it's important we should be clear-eyed about the fact that the scientific publishing is a racket. I don't see how you can say it any other way. It's ridiculous. But anyway, just some thoughts from the European perspective.
Yes, thank you for your thoughts. By the way, you often become a JJ reviewer, so I really appreciate your service to a journal. And how the fee is determined is something beyond the level of editors, but we hear you from many people that the fee is really high, but open access standards is important, so we may not want to go to subscription option. So how to make the publication fee reasonably low with open access is a major issue that we should talk about. We should talk to the people higher up. Right. Thank you.
So next up, we'll have introducing our new grand challenge for the next 3 years will be Lian Chun from your HAO, right? Are you NCAR or HAO? Okay. From the High Altitude Observatory.
Thank you, Aidan. Okay, so good morning, everyone. Thanks for joining us for this introduction to CEDAR 2026 Grand Challenge, Cross-Scale Coupling and Variability in the Upper Atmosphere and Ionosphere Pathway to Improve the Space Weather Predictability. So this Grand Challenge brings together a diverse team of conveners from across the CEDAR community, industry, and operational space weather community. Our goal is to advance understanding of how variability develops across scale in the ionosphere thermosphere system, and how this understanding can ultimately lead to improved space weather predictability. So first, I will begin with a brief overview of the introduction. I will begin by discussing the scientific motivation and the 3 science questions, and Yaga Richter will talk about NSF NCAR ESPAT initiative, Earth system predictability across timescales, and discuss why this partnership is particularly exciting for the CEDAR community. And Sudha Kamali will talk about the systems and the team science approaches we are adopting to organize the effort of this grand challenge activities. So now I will discuss the scientific motivation for this grand challenge and the scientific questions that will guide our activity over the next 3 years for this grand challenge workshop. So the central theme of this grand challenge is the predictability. How predictable is the IT system? What controls the predictability and what limits it? And before I introduce the science question, I would like to first place this effort in the broader context of CEDAR and recent advances in our community. So this grand challenge is built on several recent and ongoing grand challenge workshops, including terrestrial weather impact, gravity wave coupling, and polar patch. And together with advances across the broader heliophysics community, in observations, in theory, in modeling, in data assimilations, we have significantly improved our understanding about the processes that drive the IT variability. And we can now take the next step, and from asking what are the effects to asking how predictable are these effects. And to address this grand challenge, we use new approaches, including collaborations with NCAR ESPAT initiative and the use of systems and the team science approaches that will be introduced shortly. And to understand this predictability, it is helpful to have a conceptual big picture of how forcing is transformed to the variability in the ionosphere thermosphere systems. And one useful way to think about this is to view the IT system as an active transformer. So the IT system is constantly driven by forcing from above and below. From above, we have solar and magnetosphere forcing, including solar irradiance, auroral particle precipitation, and high latitude electromagnetic forcing. And from below, we have waves spanning scales from gravity waves to tides to planetary waves. And the IT system transforms this energy and momentum input to variability in the system through coupled photochemical, dynamical, electrodynamical, and radiative processes. And one major challenge is that we still do not fully characterize these drivers. And if we don't accurately represent this forcing, we cannot accurately predict the response. But even with the same forcing, we know that the IT system can have responding to the forcing very differently based on the characteristics of the IT system. And this including the background condition of the IT system and the processes that the system uses to distribute the energy and the momentum globally. So therefore, improved predictability requires advances in 3 areas: better characterization of forcing, and a better understanding of the background state and the response pathways, and better understanding of the sources and the limits of predictability. So these ideas motivates the three science questions of this grand challenge. So our first science question focused on the driver of the IT variability and the predictability. So we know that the system is forced from both above and below, but there is significant uncertainty remain in how these drivers are characterized and represented. From above, high latitude forcing is highly structured and variable across scales, with mesoscale forcing embedded within the larger scale convection pattern, and they constantly modulate how much do heating and ion drag input into the IT system, driving the IT system. And from below, gravity waves, tides, and planetary waves, and the secondary waves interact across a broad range of scales, and many of which remain unresolved in global models. So the key question is which driver, processes, and scales matter most for IT variability and predictability? Answering that question will help us identify where improved observations, theories, and modelings can most effectively advance space weather prediction. Our second science question focused on the response of the IT system to external forcing. We know that the same forcing can produce very different responses. The background condition, including temperature, composition, wind, plasma density, and conductivity, they establish the state where the forcing act upon. And this background state is highly variable based on with the local time, with the season, with solar cycle phases, and with the lower atmosphere forcing. And then the energy and momentum are transmitted through the IT system globally by multiple cross-scale dynamical and electrodynamical processes, linking forcing and responses across regions, scales, and times. And understand this coupling pathway is essential to understand how localized forcing impacted the IT system globally, and how same forcing can produce very different response. So ultimately, our goal is to determine how background condition and the coupling pathways control the magnitude, the timing, structure, and the predictability of IT response to external forcing. So our third science question focuses on predictability itself. So even if we improve our understanding of the driver, the background condition, and the response pathways, we still need to determine how predictable the system is and what control and limit the predictability. Address these questions require coordinated use of observations, theory, modeling, and data assimilations to characterize the evolving state of the IT system and to quantify uncertainty in the driver. And at the same time, emerging approaches such as AI and machine learning provide new ways to identify relationships, hidden patterns, and potentially missing physics that are difficult to uncover using traditional approaches such as model data comparison alone. So putting together these science questions is the science focus for this grand challenge. First, how can we better characterize and representing the multi-scale drivers that force the IT system? Second, how do background conditions and cross-scale coupling pathways regulate the system response? Third, what determines predictability and its limits, and how can we improve predictive capability? So this naturally raises a question: why is this the right challenge for the CEDAR community, and why is this the right time? So first, predictability has emerged as a central challenge in heliophysics, reflected in the recent decadal survey and growing national interest in space weather resilience. And second, the CEDAR community is uniquely positioned to address this challenge. We bring together expertise in observations, in modeling, in theory, data assimilation, advanced data analysis, and AI and machine learning across the coupled IT system. We also have access to remarkable set of community assets, including ground-based observations, satellite observations, and physics-based models. So finally, initiatives such as ESPAT provide an opportunity to connect CEDAR science with broader Earth system predictability efforts and to develop new collaborative approaches for tackling complex predictability challenge. So we believe this is the right community and the right time to take on this challenge to understand and improve space weather predictability. One of the unique aspects of this grand challenge is its partnership with ESPAT and SF NCAR's Earth System Predictability Across Timescale initiative. While our focus is space weather predictability, many of the challenges we face, like understanding complex system, cross-scale interactions, uncertainties, and predictability limits, are shared across Earth system science. And this partnership provides our CEDAR community an opportunity to learn from and to contribute to a broader predictability efforts. So with that, I would like to hand it over to Yaga Richt, who will introduce ESPAT. So this is advanced.
Good morning. My name is Yaga Richter, and I started my career by studying gravity waves, and as a postdoc, I actually was in HAO. Right now, 20 years later, I work for the NCAR Directorate, and I lead several of our strategic initiatives. One of them is ESPAT, Earth System Predictability Across Timescales, and I'm very excited for this collaboration with CEDAR. So I'm going to give you a little bit overview of ESPAT. So the motivation for this is every time you turn on the TV these days, there is another extreme weather event. Mostly on the TV you see floods, droughts, wildfires, but space weather events are also starting to appear, and there is a growing societal dependence on satellite communications, which makes space weather forecasting essential for mitigating disruptions to navigation, communication, power systems, etc. So what NCAR has done in 2023, late in October 23, is launch this initiative focused on deeper understanding of the Earth system through coordinated and collaborative research with the goal of enhancing societal resilience and enhancing predictability for a variety of phenomena. So our focus areas are subseasonal to seasonal predictability, hydrological predictability, space weather, and then also wildfires and cloud aerosol interactions. I'm going to talk a little bit about the subseasonal to seasonal predictability area because that is the one that we launched first. So this is the one we're learning from, and a lot of the structure that we have put in place for that topic, we're going to carry over to the space weather area. And to give you a little bit of my background, so when we kicked off the initiative, we first had an internal workshop at NCAR in February 24. Then we brought 500 community members to NCAR in April 2024, but that was during the time of the solar eclipse. So mostly we got Earth system predictability needs for all the other phenomena other than space weather. So then subsequently that September, we ran an internal workshop with some community members specifically focused on space weather. And you see on the slides, there are two report covers. So there's one from the broader meeting, and there's a specific one from the space weather workshop, and I'll come back to that in a minute. So since then, we've been working on the subseasonal to seasonal prediction theme, where we have about 100 community members engaged in the challenge. And if you look across the whole Earth system, including space weather, there's 3 grand challenges that were identified. They were very similar to what Liang noticed. There are interactions between various components of the Earth system, also interactions between spatial and time scales, and also interactions with external forcing. And that really applies to all areas of science. So whether you're looking at convective storms, there's interactions between the smaller scales and large scales, or whether you're looking at space weather, their problems are very analogous. All right, so our approach, the ESPAT approach, is a really interdisciplinary team-based approach. So our goal is to put NSF NCAR scientists on teams together with university researchers on really close working teams, and then also have those teams interact with the broader community. So maybe some user communities. For the lower atmosphere, that means the WCRP, so World Climate Program. For the space weather, might be the United Nations Office of Outer Space Affairs, and of course, other agencies. So one of the approaches, we create these working groups that are focused on integrating modeling, observations, data simulation, machine learning, and AI. And also a big part of SPAT is employing convergence research approach. And I'm going to talk about that on the next slide. So convergence research is a means of solving vexing research problems, especially those focusing on societal needs. And convergence research has two primary characteristics. It's driven by a specific and a compelling problem. So whether that problem arises from deep scientific question or societal need. And it requires deep integration across disciplines. So it really requires people from different fields coming together and working together to solve a problem. And it is sometimes challenging because it's difficult to communicate with people who do different work, but that is really when a lot of progress can be made when you bring different approaches together. So it's like the sum is bigger than the individual parts together. And we have right now a collaboration between the SPAT effort and our Convergence Science program, and it's led by Sudha Kamali and Julie DeMuth. And what they're looking at a pilot effort is to understand the needs of the users, and specifically those looking in space traffic management, and to look at the gaps that they're seeing in the predictions, and out of that back out the key scientific issues that are preventing that progress. So that is something that Sudha may touch on a little bit later, but that is the approach that you have these deep collaborations with people that you may not want to normally be working on to move the science forward in a meaningful way. All right, I'm going to come back to this SPAT Space Weather Workshop report. So this was going on in the fall of 2024 when the decadal survey was being written. So we didn't have the outcomes of the decadal survey at the moment of the workshop, but then we synthesized them when the survey came out. But the three grand challenges that we identified during the time was understanding the interactions across the Earth Sun system components. That's including solar magnetic eruptions, solar wind evolution, and magnetosphere, ionosphere, thermosphere coupling. Also determining how Earth system variability affects geospace predictability, and how cross-scale processes affect geospace atmosphere interactions and predictability. And again, addressing these challenges requires just a variety of tools and methodologies to come together. So advances in observations, modeling, and AI and machine learning. And actually, after we wrote the report, there was actually quite a bit of alignment with the decadal survey, and the priorities are pretty well aligned. And also a key part of the decadal survey was including system-level understanding and then developing the community and making accessible modeling frameworks and expanding DA capabilities. So I'm going to briefly talk about the capabilities that we mostly have at NCAR for this problem, and they largely evolve around modeling. So NCAR is very involved in the coupling from below and above effort with MAGE, and then WACM-X is the flagship model produced by HAO and NCAR, and that's the atmospheric component of MAGE. We also do a lot of high-resolution simulations. So Han Lee, I believe, is coming in late, but he's been running 25-kilometer simulations with WACM. And also WACM is part of the CSM, so the Community Earth System Model, so that's the low-top version. And what they're working on is a lot of kilometer scale simulations. So they're working right now on diamond-type simulations that are 3 kilometers, and they're specifically raised the lid to go all the way through the stratosphere. So in order to allow for studies of gravity waves from convection. And I think Julio Bachmeister maybe is going to be here, and you can talk to him about the details of that. But it is another platform for connecting to the lower atmospheric community. The data simulation advancements, so we use both JEDI and DART, and Nick Pedatella is here, and I think he's going to talk about that in another session. And I already mentioned the convergence research. One other thing that I mentioned, that during our workshop, we identified a need for what we call WACM-X reduced complexity. So some of you use WACM-X, but as you know, the troposphere is the most expensive part of that model. And we are working on CSM3, which is even making the troposphere a lot more expensive. So this is not very conducive to running high resolution or running numerous ensembles. And then you have time GCM, but time GCM has been a little old, and it could use a lot of the physics from Wacom X. So the idea is then to develop a reduced complexity boundary condition, so boundary driven by data, either reanalysis, model data, or AI emulation, that would be a little bit in the upper stratosphere, that would be the bottom of that model. So the status of that project is in conceptual design and requirements capturing, so we are having software engineers look into what it would take. I would mention, if that's something you would be really keen on partnering and maybe writing a proposal, come talk to me or CEDAR or anybody on the team. It is hard to get model development funded. We are going to try to do it internally, but if there is anybody who feels passionate about it and would love to help us find a source of that funding, that would be amazing. All right, so this is my last slide. So for the CEDAR SPAD collaboration, what we hope is to form working groups that will meet monthly, and then will be between the grand challenges meetings at CEDAR. And we also hope that those groups can meet at AGU or AMS, just to keep the conversations going. And we're envisioning 3 groups corresponding to the 3 key science questions, but we'll see how the breakout groups go on Wednesday, and sometimes when people get together and refine questions, maybe we'll end up with 4 or 2. It doesn't really matter. I think the idea is to make this work for this community, and how many of our groups we need to have, that's what we're going to have. For the subseasonal to seasonal prediction topic, what works well is we have 1 NCAR co-chair, co-lead of those groups, and 1 external one, and we just set telecon dates to be monthly, and then people can make progress and discuss between the meetings, and then always meeting at AGU or at CEDAR in person is great. And then each group would agree on specific outcomes, deliverables, and work together throughout the year. All right, so that's all I have, and I'm going to pass it on to Sudha Kanmali, who's going to talk a little bit more about this team-oriented approach.
Hi, everyone. I'm Sudha Kamali. I'm a research engineer at HAO, and now working with the DO at Yaga on this more cross-disciplinary projects, and one of the conveners of this grand challenge. So I'd like to touch a little bit on 2 areas that both Li Ying and Yaga talked about, and that's taking a systems approach to studying the geospace and the heliophysics, and also what that means is that we need to take a team-based approach. And so I'll start by just a reminder of the decadal survey and the focus and its urge that we should look at the heliophysics as a system of systems. And if we want to understand it as a whole, we do need to study each of the components, but also look at the interactions between them. And for that, we're really looking at the natural system, the sun, and all the medium between the sun and the earth, the upper atmosphere, magnetosphere, ionosphere, thermosphere, all of that together. But if we take a step back, we realize the natural system is only part of the larger system of systems. And so the other part of this system of systems is a technical system. And when I mention the technical system, I'm really talking about the scientific systems and engineering systems that the community is putting together in order to study, understand, observe, model, and just analyze the natural system. And when we talk about technical system, we could also include the infrastructure in society and the communication system and all of that, but that's not what we're focusing here. It's really your technical systems developed by the scientific community to understand space weather and the geophysics more. And so if we take a step back from that, and I would want to say this was also mentioned partly in the decadal survey, but also in a white paper that came before that, I believe by Woolridis et al., and if I didn't pronounce that name correctly, I'm sorry, but they did talk about taking a system approach to our technical systems, our observation systems, our modeling system, and how can we work together to really help us accelerate our understanding of space weather. Now, if you take a step back, I'd like to say that there's also a 3rd component in this system of systems, and that's the social system. And a lot of the times when we talk about social system, we think of end users. As scientists, that's what we see as a social system. But here, and they are important, they're a big part of this, but we are also really need to think about our own scientific community as that social system. If we want to use, design, and develop technical systems in order to study the geospace as a system of systems, we need to start to think about how do we want to organize and coordinate and collaborate as well. And I wanted to talk here about the Conway's Law. You might have heard this. It came out in the software engineering system world, but as time has moved on, they've realized this really applies to any kind of system. And what Conway says is that organizations which design systems, any kind of systems, are constrained to produce designs which are copies of the communication structure of their organization. So if, as a scientific community, we want to start to look at the natural system as a system of systems, and we want to look at how are we going to put our technical systems together, ground-based observation, space-based observation, how do we want to couple it with modeling, AI and machine learning, we need to understand that we are constrained by the way that organizations are now communicating, collaborating, and convening. And so with that in mind, we do need to think about how do we want to coordinate more. And this is where the team science, team-based approaches, convergence research that Yaga touched on really becomes important, because there's a body of knowledge out there that shows us better practices, heuristics, lessons learned, frameworks that we could put in place that could help us work together more effectively. And because this is not something they teach us in grad school, you're taught to really work on your particular area of expertise, and that's really important and it's needed. But if we're starting to now work across disciplines and we need to communicate with each other, we need to look at different ways of doing that, how to do it effectively and smoothly. And I did want to briefly touch on the team science definition that is in the National Academies of Science, Engineering, and Medicine report, which is a collaborative effort to address a scientific challenge that leverages the strengths and expertise of professionals oftentimes trained in different fields. And this is a more general definition of, with convergence, we go a little bit deeper in how we collaborate, but with team science, I would say that's the early stages of how do we come together, how do we communicate and work together effectively to understand this natural system and use our technical system together. And so I'd like to end by just highlighting what Lee-Yin said, that the CEDAR community really holds the expertise to look at these scientific questions that were put together and really connect the predictability of the upper atmosphere geospace to both the lower atmosphere and the larger heliophysics community. And SBAT, as Yaga mentioned, has experience looking at team-based approaches, systems approaches in other areas of Earth system science that we can learn from and adapt and apply it to this particular grand challenge so that we can work collaboratively towards improving our understanding of space weather. And so I'd really like to invite you to join us in the coming days as we come together to refine the science questions that Lee-Yin introduced and also talk about better ways of perhaps collaborating. We have 2 upcoming breakout sessions, one Wednesday morning, one Wednesday afternoon, and they've been deliberately put together so that we have a chance to talk across disciplines. So in the morning, we have a cross-disciplinary panel discussion with people from backgrounds in AI and machine learning, modeling, data assimilation, observation, talking about this grand challenge from their particular perspective and finding ways that we can collaborate. And in the afternoon, we have individuals from different organizations and sectors coming together and talking about the grand challenge and discussing how we can work across sectors. And also, we are going to talk about relay races and batons. And if you want to learn a little bit more about that and how it's related to a CEDAR Grand Challenge, you're going to have to join us that Wednesday afternoon, and Lynn will talk us through that. So with that, I'd like to thank you for giving us an opportunity to introduce this Grand Challenge this morning. And I hope you join us on Wednesday. And if you have any questions, Lee-Yin, Yaga, and I could help answer. I think we left quite a lot of time for that. Yeah. Thank you. Do you have any questions?
We have lots of time for questions.
Yeah. And if not, we're around. There's
I'm
one
here.
question. Yeah.
One question. Well, not a question, but more of comments.
Yeah.
You can predict what you can observe. And if we compare ourselves to the NWP systems in the lower atmosphere, they can use millions of observations daily. We don't come anywhere close to those numbers. And so as a community, we should also push for more missions to observe the upper atmosphere, the geospace, or whatever. Also, one important aspect is also the metrics, because that will help define or distinguish what is necessary from a scientific point of view or what is more important from an operational point of view, because sometimes they don't even coincide. So,
Thank you so much for both of those comments. Yeah, as we've been talking more and more with people, we're realizing, you're right, that there is not a lot of observations, and yes, we need more of that. And then at the same time, how can we make more use of what we already have? Are we really doing that? Or is there other ways to use it? Definitely.
Thank you for the introduction. So we know that NCAR has been developing those fascinating models for years, and our whole community is benefited from using the models and help us answer science questions. So this is a great opportunity for CEDAR and NCAR can kind of work together, and the predictability is one of the most important topics in the future for space weather. I just wanna, I'm wondering if you could elaborate a little bit more on how these working groups you mentioned would really work, because maybe in the future this can lead to, because I know GEM working groups are also highly associated with funding opportunities for people. So for CEDAR, I'm not sure, maybe in the future working groups can work together to propose and, with the agencies here. Could you say a little bit more of that?
Definitely. And I think Yaga touched on it in the S2S group, the subseasonal to seasonal category. When they brought people together, just having that opportunity to talk through it, discuss it, it did bring out opportunities for writing proposals, I believe, Yaga, papers, collaborative papers, and just shared knowledge that started to help people think in different ways and apply to different opportunities that they might have not thought before. And what I understand is that they meet once a month or every 6 weeks, depending on what works for the group. But the point is that it's constantly, you have to show up and be committed and meet. And that communication and relationship has been building up towards these opportunities then organically happening. And I don't know, Yaga, if you wanted to talk a little bit more, since you've been more involved with that, to share a little bit more with that.
Yeah, I think Suda got it exactly right. So as you start coming together with people, then you start coming up with ideas. And out of the working groups that we put together, we have spun off another workshops that are funded. And there have been several proposal calls that have been put together. So yes, we do hope that this community, the same thing would happen. And some of the NSF calls NCAR cannot apply for, but we are always happy to take visitors and postdocs to have them sitting at NCAR for anywhere from a couple of weeks to several years, just to foster those collaborations. So that would be a great way. But yeah, as Suda says, just bringing people together, regularly exchanging information, then you find common interests, and then you can move those forward.
Yeah, I remember I once attended a NASA town hall, and I think from that town hall I got 2 points, important points. One is NASA is wanting to shift towards a larger proposal, and the other one is NASA wants to be able to be, for the fundamental research, to be able to transfer to application in easier, faster way. So I got these 2 points, and I think as for to answer your question, when we don't know, what opportunity will come up as a NASA proposal call, what they will come up. But I think that's a guideline, as so this is naturally, it's like interdisciplinary, require, it's solve this predictability require like a different expertise. And so when the opportunity comes, then we apply for that, for bigger team, for more towards easier, faster transfer to the for fundamental research to application. So that's my 2 cents.
So I'll add one more thing. So for other areas at NCAR, because of the federal funding, we are also heavily exploring different foundations. We've not started exploring them for space weather, but especially there's a lot of opportunities in the area of AI machine learning. So again, that could be maybe a subtopic that emerges, and there is definitely money there. So Google had just challenged AI for science, and space weather was in scope of that. There's the Schmidt Foundation funds a lot of that. So there is other areas and other people coming around the table to help with the general scientific funding. You just have to have new ideas, and they have to, for the foundations, they really have to be at the forefront, and AI machine learning seems to be one of the topics there.
If we could have one more round of applause for our new Grand Challenge introductions. So we are running a little bit ahead of schedule, but as long as Jens Oberheit is ready, we will move on to our Grand Challenge report for our sort of summary the impact of terrestrial weather on the space weather of the ITM. And if we get that done early, on time, and then go through the memorial, then we can release everybody early to lunch. Yay! So, applaud for him.
Okay, good morning, everyone. I'm Jens Oberheit from Clemson University, and I'm ready to give the presentation. Okay, so we are in year 3 now of this grand challenge here about impact of terrestrial weather on the space weather of the ionosphere, thermosphere, and mesosphere. And what you see here on my title slide, that's some work that Pavel Inchin and co-authors did in 24. And this kind of summarizes, as I think, quite nicely without too many words, what this whole thing is about, okay? So you basically look at maps of North America, okay, continental United States. That's a winter storm event in December 22. So the winter storm was called Elliott. I'm from the beautiful state of South Carolina, and I can tell you it was really cold there. That's so it was basically a continent-wide winter storm. So the color map you see on the left, these are basically wind speeds, surface winds, very high. And the surface winds blew over mountains and other things and triggered a whole spectrum of both acoustic and gravity waves. That's what you see in the center panel. These are satellite-borne measurements, essentially in the stratosphere from the AIRS instrument. And then finally, the manifestation in the ionosphere is on the right from GNSS observations. And so we can really make, just by looking into the data here, a very conclusive argument what really these big continent-wide weather events we have in the troposphere do to the upper atmosphere and to the ionosphere. And so this whole Grand Challenge workshop was about, or it still is about, advancing the understanding of whole atmosphere interconnections between terrestrial and space weather, and to do that through a combined modeling and observational efforts across different spatial and temporal scales. So when we proposed this Grand Challenge workshop, we basically had the concept, well, in the first year, let's collect what observational modeling baselines we basically have. Let's look into year 2, what can we do in terms of model data comparisons across scales, and what can we do in terms of data assimilation. And in the end, that's pretty much what we did. That's The workshop was, I would say, well attended. In year one, we had more than 90 people. Even last year, when the Grand Challenge workshop was Friday afternoon, not necessarily the most popular timing for attending a conference, we still had more than 70 people in this workshop. And this year, we finally move towards a more detailed discussion of the physical mechanism, so kind of merging all the observational modeling efforts and data assimilation efforts together. And so we have 4 hours basically tomorrow. Okay. So these are some of the data and models we discussed in year one, back in 24. This is not a complete list. And I'm not going to read all these wordy tables there, but we basically managed to publish at least a subset of the model and observational results in a Surveys of Geophysics article, and you see the citation here. And so I encourage you to have a look into that. And because we briefly discussed matrix, so this whole paper also discusses a lot of matrix data model comparison matrix, what is available, what is good for what case, and what do we need to do better. So in year two, the focus was on data assimilation. This is an example what was shown in terms of initial GEOS MLT results that was presented by the GEOS MLT team by Josh Petit. And so GEOS MLT is basically an upward extension of reanalysis. Okay, so the goal, final goal is in the end to have a kind of reanalysis data set that goes way into the thermosphere. And Fabrizio Zassi and co-workers will give an update on that tomorrow, what the status is. We also used, or there was also a slightly different approach to data assimilation, basically constraining an empirical model with observations from the TIMET satellite and then comparing it to a general circulation model simulations, and with particular emphasis on the energy flux that comes from atmospheric tides from the lower atmosphere into the upper atmosphere. So I'm a physicist, and that means when we talk about coupling, lower upper atmosphere coupling, so what really matters for me as a physicist, and I'm sure for most of the community, what's really the kind of energy and impulse fluxes that really matter here. And so this is work that was presented by Mukta Neogi, my own student, looking into the energy fluxes from the tides. And actually today, later this afternoon, in Shan Lu's session at 4 o'clock, she will give an update on that, where she also included gravity waves and planetary waves, really to have the full wave spectrum in terms of coupling here. So now I would like to spend a few minutes to give you a little bit of a teaser for tomorrow. So these were all slides that the presenters, or some of the presenters for tomorrow's workshop provided. So this is work from Manbarat Dudley and his colleagues. So you might be aware that NRL is currently working on an updated version of both EMSIS and HWM, and one of the updates that's included is that the new versions of these models now also account for non-migrating tides. It was not the case in previous versions. And what Manbarat did here is he basically used the current version of EMSIS and HWM and the new version that's still under development or final testing right now, and basically coupled that with SAMI 3, and then looked into what are actually the consequences from the empirical modeling point of view for the ionosphere if you include non-migrating tides in the neutrals. Basically, that's all stuff that comes from the lower atmosphere and not. That's what you see here. So the left column are different ionospheric parameters without non-migrating tides. The center column is when non-migrating tides are included, and the right column is the difference in percent. And you see that there are large regional variations in electron densities, TEC, and so forth, of up to roughly plus minus 30%. So the bottom message here is that including the non-migrating tides in HWM and EMSIS is not only important for the neutral atmosphere, but also has a lot of consequences for the ionosphere. And so Mambarat will talk more about that tomorrow. So this is more a mechanism study from Jiarong Sheng from Utah State University. Jiarong will talk about what impact sudden stratospheric warmings actually have on the semi-annual oscillation in the mesosphere. And Jiarong looked into the Javara reanalysis data set, so that's the Japanese upper atmosphere reanalysis there. And she will explain the mechanism how the strat warms significantly intensify, particularly the westward stratospheric SAO phase. This is a result from OR, gravity wave measurements from Ben Martinez. So Ben was a Clemson student. He just graduated. He's now a postdoc at Utah State University working on gravity waves. And he basically looked into the intensity and magnitude of gravity waves observed by ORS during SSW events. So you may have seen the left figure in a publication before, but this was for the Northern Hemisphere. But the OR team is now also looking into the Southern Hemisphere. That's the right figure. And basically, they find consistent results that OR observes weakened gravity wave activity around the mesopause following the onset of the sudden stratospheric warming both in the northern and southern hemisphere. So this is a result that Shantanap Duri will present a comparison between MAGIC Gemini observations of gravity waves and ionospheric responses. That's what you see on the right-hand side with observations, GNSS, and particular also observations made at Millstone Hill from the incurrent scatter radar. And basic finding is that from the modeling point of view, the response is a little stronger than what you see in the observations. Part of that might be due to slightly elevated geomagnetic activity levels, which also points to this interplay between forcing from above and from below, that we can't really look into that independently. And Shantanap will talk a little bit more about the physics behind that. And so finally, these are observational results from John Merriweather and co-workers. What you see are observations from the Fabry-Perot in Argentina at El Leoncito, basically a comparison between vertical wind oscillations and in the second panel from top, the simultaneous observation of ionospheric oscillations visible in GNSS data, and at least part of what we see here can be connected to orographic gravity waves, but Dr. Merriweather will talk more about that on Tuesday. And finally, this was only intended to give you a little bit of a teaser. There was no time to show more of these results, of course, so this is a complete list of speakers and topics there. And I hope most of you will be sufficiently interested to come and join the discussion. Thank you.
questions? Okay, looks like we will halt there. Thank you. So we're going to give it up for
All right, everybody, before you go to lunch, and Jens, I think you left your glasses up here. We're going to take just a few minutes to pay tribute to the very first CSSC chair. He passed away last fall. So Jerry G.J. Romick got his bachelor's in physics at the University of Alaska Fairbanks in 1952, his MS in physics from UCLA in 54, and his PhD from University of Alaska Fairbanks in 64, where he taught for 23 years, earning the title Professor Emeritus. Professor Romick was one of the original founders of the CEDAR program. He served as the first chair of the CSSC from 86 to 88, and then the NSF program manager for CEDAR from 88 to 90. In the early days of CEDAR, Jerry used his wit and optimism to persuade community leaders within the CEDAR program to work together in harmony. Sounds like a really cool guy. Observing optical emissions led to an understanding of the data, which gave him a knack for coming up with productive hunches, which stimulated directions for new theoretical work and observational programs. This led to work with scientists at Johns Hopkins Applied Physics Lab in their satellite programs. He retired from Johns Hopkins in 2000. Jerry was an avid hiker and swimmer, quick-witted and fun-loving. He had a life filled with family and food. His wife of 71 years passed 2 weeks after his death. He is survived by 6 children, 15 grandchildren, and 13 great-grandchildren. And I love this. He taught his kids to always try to fix something yourself, because if it's broken, you can't make it any worse. Seems like a good motto to embrace in every aspect of life. He is fondly remembered by all those who worked with him in the geophysical and space sciences community. In remembrance, his family suggests hugging your favorite scientist and always taking your hunches seriously. Thank you.